9. Supervised learning, training an AI model on data that has been labeled with the correct answers. Like using flashcards with questions and answers to teach a student. This is used for prediction tasks, like forecasting sales or house prices. Powers email spam detection, where emails are labeled spam or not spam. The most common type of machine learning used in industry today. 10. Unsupervised learning, training an AI on unlabeled data to find hidden patterns and structures on its own. Like asking a student to group different types of animals without prior knowledge. Used to segment customers into different marketing groups based on behavior. Can discover anomalies, helping in fraud detection or identifying system errors. It's about data exploration and discovery, not just prediction. 11. Reinforcement learning, RL, training an AI agent to make decisions by rewarding it for good ones. How you would train a dog, giving it a treat for a correct trick. This is the technology used to train AI to play complex games like Go. Powers robotics, teaching a robot to walk or grasp objects by trial and error. The agent learns a policy or a strategy to maximize its total reward. 12. Model the output of a machine learning algorithm. It's the brain that makes predictions. It's a mathematical representation of the patterns found in your data. A trained model can take in new data and predict an outcome. Examples include a spam filter model or a stock price prediction model. The goal of training is to produce a model that generalizes well. 13. Training data, the dataset used to teach or train the machine learning model. The quality and quantity of your training data determine your model's success. A model is only as good as the data it learns from. Biased training data will lead to a biased and unfair AI model. It's the historical information from which the model learns its patterns. 14. Testing data, a separate dataset used to evaluate how well the trained model performs. This data has never been seen by the model during its training phase. It's like giving a student a final exam on topics they've studied. Good performance on testing data means your model can generalize well. Prevents you from being fooled by a model that just memorized the training set. 15. Overfitting, when a model learns the training data too well, including its noise and quirks. Like a student who memorizes test answers but can't solve new problems. Your model performs perfectly on training data but fails badly in the real world. It learns the noise, not the signal, making it useless for future predictions. Prevents AI from generalizing its knowledge to unseen, real-world situations. 16. Underfitting, when a model is too simple to capture the underlying patterns in the data. Like a student who didn't study enough and can't answer even easy questions. The model performs poorly on both the training data and the testing data. Indicates your model needs more complexity or better features to learn from. Your model is not powerful enough to understand the data's structure. 17. Bias-variance trade-off, the fundamental challenge of finding a balance between overfitting and underfitting. A simple model has high bias, underfits. A complex one has high variance, overfits. The goal is to find the sweet spot with the lowest overall error. This trade-off is a central theme in all of supervised machine learning. It's a constant balancing act for every AI developer. 18. Feature and individual measurable property are characteristic of the data being observed. In predicting house prices, features could be square footage or number of bedrooms. Also called a variable or an attribute, it's a column in your dataset. Choosing the right features is one of the most important steps in ML. It's the input signal that the model uses to make a prediction. 19. Feature engineering, the art and science of creating new, informative features from existing data. Can dramatically improve a model's performance more than a better algorithm. For example, creating a debt-to-income ratio from separate debt and income features. It requires creativity and a deep understanding of the problem domain. Good feature engineering separates great models from average ones. 20. Label the answer or the output value that you are trying to predict in supervised learning. For a spam filter, the label for each email is either spam or not spam. In a house price dataset, the label is the final sale price. The model learns the relationship between the features and the label. Unsupervised learning works with data that has no labels. 21. Classification: a supervised learning task that predicts a category or class label. Is this email spam or not spam? Is this tumor malignant or benign? The output is a discrete category, not a continuous number. Algorithms like logistic regression and support vector machines are used for this. It's about sorting items into predefined buckets. 22. Regression: a supervised learning task that predicts a continuous numerical value. What will the temperature be tomorrow? How much will this house sell for? The output is a number on a scale, not a fixed category. Linear regression is the simplest and most common regression algorithm. It's about fitting a line or curve to your data points. 23. Clustering: an unsupervised learning task that groups similar data points together, automatically segmenting customers into groups based on their purchasing habits. It discovers the natural clusters or structures within your dataset. The k-means algorithm is a popular and intuitive method for clustering. Unlike classification, the groups are not predefined, the AI finds them. 24. Dimensionality reduction: the process of reducing the number of features, dimensions, in a dataset. Simplifies the model and can help it run faster and more efficiently. Can also help visualize high-dimensional data in 2D or 3D plots. Techniques like PCA, principal component analysis, are used to achieve this. It's about finding the most important information and discarding the rest. 25. Gradient descent: an optimization algorithm used to find the best settings for a model during training. Imagine walking down a hill blindfolded. You take small steps in the steepest direction. It iteratively adjusts the model's parameters to minimize its prediction error. It's the engine that powers the training of most deep learning models. The learning rate, alpha, determines the size of the steps you take downhill. 26. Loss function, cost function, a function that measures how far off a model's prediction is from the correct answer. A high loss value means the model is making big errors. A low value means it's accurate. The goal of training is to minimize this loss function. Gradient descent is the tool used to find the minimum of the loss function. Different tasks, regression versus classification, require different loss functions. 27. Hyperparameter tuning: the process of finding the optimal settings for a learning algorithm itself. These are settings you choose before training begins, like the model's complexity. It's like tuning the knobs on a radio to get the clearest signal. Can have a huge impact on the model's final performance. Often involves a lot of trial and error or automated search techniques. 28. Cross-validation: a technique to ensure a model's performance is stable and not a random fluke. You split the data into multiple folds and test the model several times. Gives a more robust estimate of how the model will perform on new data. It is a powerful tool to prevent overfitting during model selection. It ensures your final exam results weren't just due to an easy test.